Hello, welcome to Maths with EJD. This is the second video on numerical analysis, especially the introductory part. In the previous video, we had talked about, we had considered an overview of common numerical methods. So here we are looking at error analysis because, of course, if you are using numerical methods to solve problems that are difficult to solve, that don't have closed form solutions, or, or who are difficult to, whose answers are difficult to arrive at, right? Definitely, you're just approximating. So error analysis becomes very useful. So you have to know to what extent do you want to approximate. And that is why error analysis is really crucial. And the essence of this lesson is to understand the different types of errors that occur in numerical computations and how to quantify these errors. So let's go to the introduction of this. So for the introduction now, um, in numerical analysis, in numerical analysis, errors are inevitable. Errors are inevitable because we are only approximating, right? Errors are inevitable because of approximations, and computational limitations. Computational limitations. So understanding the types of errors and their impacts on calculations is key to assessing the reliability of numerical methods. Okay, so let's talk about types of errors since you've mentioned that already. Types of errors. So the first type of error we'll talk about is absolute error. Absolute error. Okay. So this is the difference. Absolute error is the difference between the true value, which we can call T, and the approximate value, true value and approximate value, which you can call A. So that is the absolute error. So in this case now, we can define absolute error. So you see the absolute error is equal to the absolute value of T minus A. Okay. So if we are going to take an example, we know that pi can usually be taken to be 3.14, 3.14. Okay, let's assume, right, that um the how do I put this now? Trying to get something. Okay, okay, no problem. Let's say that a particular quantity, let's call it Q. So let's say the true value of a value Q is 3.71, while the approximate value is QA. Okay, approximate value is now say 3.62, maybe based on some kind of approximation. So you can say that the absolute error is actually absolute value of 3.71 minus 3.62. So in that case, we don't care about the sign of the difference. We just want the actual difference. And this will simply be the absolute value of 3.71 minus 3.62. Of course, that should be 0.11, and that is 0.1. That would be 0.1 because we're talking about the absolute value. So even if this was negative, right, it doesn't make any difference. We just want the absolute value. In fact, we can switch it over, right? Yeah, I mean, let's leave it this way. Even if it is negative, we just want the magnitude. We don't care about the sign. That's why it is absolute value. Okay. So that is the idea of absolute error. Now we have the second type of error, which is called the relative error. Relative error. So we've talked about absolute error already. So relative error now. So the the relative error actually is this is the absolute error normalized by the true value, normalized by the true value. So what this does that it tells us how significant it tells us how significant it tells us how significant the the error tells us how significant the error is compared to the actual value, compared to the actual value. Okay, so for instance, if you take the example we had the other time, that q of true value of q is 3.71, right? 3.71. I think this was wrong, right? 3.71 minus 3.62 should be, I think, 0.09. Yeah. 3.71 minus 3.62. Yeah, this is 9 and this is 0. Okay, so that is 0.09. Apologize for that. So that is 0.09. 0.09. So that is just 0.09, like that. Okay, so QT is 3.71 and actual value QA is 3.62. So the relative error, it will simply be QT minus QA, absolute value of that, right, divided by absolute value of QT, the true value. So that would be what we had the other time. Already we had, this is QT minus QA. So that is 0.09, right? So that's 0.09 that we got before, divided by the true value, which is 3.71. So we are getting that as a percentage of, or as a proportion of what we had previously. So the relative error in this case would just be the relative error is 0.09 divided by 3.71. 0.09 divided by 3.71. So that is approximately, of course, 0.024 0.02426. That's to 5 decimal places. That's the relative error. So when you normalize the absolute value with the true value, the absolute error with the true value, then you get what is called a relative error. Okay. So we have absolute error, relative error, and finally we have what we call the round of error. Round of error. Round of error. Round of error. So for the round of error, right, this occurs due to the limited precision, of computer numbers. For instance, if you're using a calculator, for instance, right, different calculators have different capacities of decimal places they can have. So because of that, so you can get different degrees of error depending on the machine you're using, maybe a calculator or a computer. So this occurs due to the limited precision of computer numbers. Imagine, for instance, so for instance, representing a number like pi. If we represent pi as 3.14, this will introduce, representing a number like pi as 3.14 introduces round of error, because pi has more decimal places, right? So if you make it, whatever you call it, it's introduced a level of round of error. Okay. So, if you look at all the so if you can get a grand example now. Okay. Imagine something surrounding pi. So we know that true value of pi is true value is that pi is equal to 3.1415926.535. So 3.1415926.535. I mean, that's not even the most accurate, most that I mean, it can keep going, but if you assume that that's the true value, right? And we now say the approximated value, approximated value, we now have that as A. That's 3.14. That's what we have most times. So we call it 3.142. Okay. So in this case, automatically by doing this, we already automatically have a kind of round error automatically, because this is the true value, this is the approximate value. So there's an error because we have cut off all the decimal places afterwards. So now we have to deal with that. So now imagine automatically your absolute error will be equal to pi, absolute value of pi minus A, the true value and the approximated value. So that'll be absolute value of 3.1415926.535 minus 3.14. Okay, so that will be absolute value of 0.00, 314. So it stops here. So every other thing goes to zero. Then we just have 0.0015926.535. So that the absolute error is 0.0015926.535. Okay, that's the absolute error. So what about the relative error? Relative error. So here the relative error would just be absolute value of pi minus true value of pi over the approximated value all over the absolute value of the original pi. Okay, so that is going to be I mean, absolute value of pi minus A is what we've got here already. So that's 0.0015926.535 divided by 3.1415926.535. And all of that is going to be approximately, I hope this is correct. I mean, when you're doing numerical analysis, you need your calculator handy, especially in an exam situation. You need your calculator handy because you have to punch your calculator a lot. So should I take the pain to do this and be sure, like double check what I already have? That is 0.0015926.535 0.0015926.535 0.0015926.535 3.15926,535. So you have to double check. So you have 3 points divided by 3.14, 1415926,535. Okay. 3.1415926,535. So yeah, so that is approximately 0.000, okay, 0.000507. That's the relative error now. I mean, even that is approximated already. So it's like all of that. Of course, we also have the idea of propagation error, right? Which means that because you have I think I should talk about that. I think I'll talk about that in a minute. But so this is relative error. Then the idea of rounding error automatically has taken place here because if the actual value is this and you make it this, so there's an error in rounding already. So, and that error, we've talked about the absolute one and the relative one. So, so I think let's talk about um, propagation error. And I think that should be the last I'll talk about. There can be other types of error, definitely, right? You know, I mean, we can extend it and begin to talk about human error and things like that. So, but let's talk about propagation error. Propagation error. I think that is worthy of mention because if you actually if you are doing if you round off a number at some point and you now use that rounded value to do another computation, it automatically will have to, affect your solution like that. All right. So let's talk about propagation error. That's really important. Three, I mean, four now. We've talked about absolute error, um, relative error, rounding error, and now I want to mention propagation error. Propagation error. So for propagation error, right? This refers to the accumulation, and amplification, accumulation and amplification of errors in numerical computations. In numerical computations. Okay. Uh, as intermediate results, are used in subsequent steps. Intermediate results are used in subsequent steps. So a classic example. So consider using the trapezoidal rule, which we are going to see later, using the trapezoidal rule to approximate integral from 0 to 1 of e raised power x dx. Okay, if you consider this situation, right, you should know that the true value, because of course we have the closed form solution of this particular x value. So the true value is integral from 0 to 1 e raised power x dx. So by the time you finish integrating, you get e minus 1, and the result is approximately 1 point. If you can integrate e raised power x and substitute 0 to the interval, so you have approximately 1.71828. Okay, that's what you get there. So, but this is one thing. So the other part is approximation. You can also get the approximation. You can get the approximation. using a single interval. Using a single interval. That's when you do approximation like that, you use intervals. So in that case, the approximation is now something like this. Approximation is equal to half into f of 0 using trapezoidal rule into f of 1. I mean, half into f of 0 plus f of 1. So that this is now half into 1 plus e. Okay. And everything ends up giving you approximately 1.85914. So you can see there's already error. So this is the real thing, but this is the approximated thing because of trapezoidal rule. So, but then this is where the approximation error comes in now. So approximation error now comes in here. If this approximation that we just have, if this approximation is used as input, so if you now use this value of that integral, if this approximation is used as inputs for further calculations, like e.g., solving another equation. If you use this x value to solve another equation, solving another equation, okay, the propagation error can compound, okay? More like you've made an error, so the error keeps compounding. The propagation error can compound, resulting in significantly larger deviations in the final results. And that's why in a numerical analysis class, you can have two students getting totally far apart results just because of how they are rounding their values in the process of their calculations. So I come to the end of this. Now, this idea of propagation and all the rest is what will make us look at the third lesson, where I'll be talking about approximations and precision. So you want high level precision as much as possible, and of course you want to have like a tolerance limit and things like that, so you can actually get the kind of so minimize your error as much as possible. So if you don't want to miss out on that, you need to subscribe to the channel and hit the notification bell so you can always get alerted each time a new video is released. Also, comment, let me know how helpful these videos are for you, and let me also know if you want me to solve a problem or teach a particular topic. Then like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.